Let's do problem 8 on the constant velocity worksheet. And here's the constant velocity worksheet. And we want to do number 8. So let me read it out loud. It says, a motorcycle starts at the origin and moves with a constant velocity of 10 meters per second for 4 seconds. Then suddenly shifts to a constant velocity of 15 meters per second for 6 seconds. Draw a velocity versus time graph. What is the area of the graph and what does it represent? And C, draw position versus time graph for the motorcycle. Okay, so let's see. Here's what's given. So we know that the velocity equals 10 meters per second for t equals 0 to 4 seconds, and then the velocity equals 15 meters per second for t equals, well, we're going to instantly change it at 4 seconds and go all the way out to 10 seconds. Oh, because it says for 6 seconds. So that would take us out to 10 seconds. And so we want to find A, we want to draw velocity versus time graph. B, we want to know what is the area underneath that graph, what does it represent? And C, we want to draw a position versus time graph for the motorcycle. Okay, now let's solve it. Now for A, we want velocity in meters per second versus time in seconds. We want to go 0 through 10 seconds. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2, 4, 6, 8, 10. And then the velocity, well, we have 10 and 15, so I'm just going to go 5, 10, 15. So it's 10 meters per second from 0 to 4. It's constant. And then some miracle happens and you immediately jump up to 15. Now, obviously, it would actually take time to accelerate to that new speed, but we're just, for the sake of keeping things simple, we're just going to say that the velocity versus time graph looks like this. So that's A. And notice what you need to have. You need to label it with units and then have increments that make sense, and then, plot the graph. Now, the area underneath this graph, we've got two rectangles. We have a delta x1 and delta x2. And so this is for part B. And that's what the area represents, is displacement. So I'm just going to start off delta x1 equals, well, we went 10 meters per second for 4 seconds. 10 meters per second for 4 seconds. So that's 40 meters. And delta x2, well, that's, we went 15 meters per second. But we did that for 6 seconds, from 4 to 10, so that's a delta t of 6 seconds. So that's 90, I believe. So the total displacement is equal to 130 meters. And that's displacement. Is what that represents. Now for part C, I'm going to draw it like this. I'm going to draw this right parallel to this. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this is going to be position. Now, the maximum I'm going to go is 130. So we might as well go like 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130. So I'll go 20, 40, 60, 80, 100, 120. And this is position in meters. This is time in seconds. And look what we did. We had a constant velocity that for the first 4 seconds of 10. So that means at 4 seconds, and I should have drawn the time axis a little better, but it's going to start at 0. Now, this was kind of given. It kind of told us in the problem that at t equals 0, we were at the origin of the position versus time graph. And then after 4 seconds, we were at 40 meters. So this has to be a straight line. Because this is a constant velocity, that means this has to be a straight, constant slope. And then at 10 seconds, well, we're all the way up at 130. So you draw another straight line like this. So I really wanted to see 2 straight lines with labels and all that. So big picture, what's the point of this? Well, it's kind of got a kinematic stack going here. If I give you a velocity graph, you can figure out what the position graph is, as long as you know what the starting position is. And that the area underneath a velocity versus time graph is displacement, or how much I changed my position. I changed my position by 130 meters. Okay, any questions? Okay, that is all.